of polynomial functions. Graphs of polynomial functions. I bought some new markers because my pens were killing me. I like colors. All right, so what is a polynomial function? And I don't want you to be scared by what I'm about to write, because I always think when I first saw this, I think it looked so crazy to me, but it's just notation and math people being math people. But P of X equals A sub n x to the n plus A sub n minus 1 x to the n minus 1 plus dot 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 A sub 1x plus A sub 0. And all this is saying is I can have a polynomial. My highest degree goes here. So if this was a 5, then I'd have a 4, then a 3, then a 2, then a 1, and then I'd have my constant term at the end. This is my constant term. Constant meaning like a number, 7, 5, negative 12, whatever. Okay. This is also your y-intercept, always. This is going to be your y-intercept for a polynomial function. Meaning if I were to plug 0 in for x, all of these would go to 0, 0, 0, 0, 0, and then you'd have that guy left over, and he would be your y-intercept. Okay? This front guy is who we're going to be concerned about tonight. This A sub n is called your leading coefficient. And you're going to want to look at him. He's going to tell you things, okay? If he's positive, he's going to tell you something. If he's negative, he's going to tell you something, okay? So we definitely want to take a look at him. But he's the leading coefficient, and this is the degree. This is the highest degree. He always is with the highest degree. And you know, on homework tonight, they're going to mix it up. They're going to put this guy back here and move it all around. Don't freak out. Just look for the highest degree, and that number in front, which we call A sub n, it will tell us things, okay? So some of the degrees that you're probably familiar with, you've done quadratic. That's what we spent a lot of the last chapter on. But let's talk about cubic functions. So cubic functions are what's called a third degree, or degree 3. That means that right there, the exponent with the x would be an x cubed, a cubic function, okay? So we would write it like this. P of x equals ax cubed plus bx squared plus cx plus d. And you can't let your a be 0 because then you have a quadratic. So that's what that little piece of information does. But cubics are fun. They look like this. Most of them like do this little like dance in the middle. You can go like that way. It can reflect it. It can be really exaggerated that way, or it can be really exaggerated this way. Those are all cubics, okay? All type of cubic functions. And they'll ask you that, like, they'll actually give you these pictures, and they'll be like, which one is a cubic function? They'll give you this. They might give you a parabola. So it's really nice and easy for homework tonight. This, the next one is quartic functions. Quartic functions are degree 4 or fourth degree. And that would be a polynomial that looks like this. Ax to the 4th plus bx cubed plus cx squared plus dx. What letter am I missing? E. Oy. And again, a can't be 0 because then you'd have a cubic function. So quartic functions are kind of funny looking too. They look like a parabola. Surprisingly enough, they have like this long exaggerated part right here, and it might go the other way. My favorite kind of quartic functions are the ones that look like W's, like that, or M's. And those are quartics. So now in your brain, you know what a quadratic looks like. It's a parabola up or down. But then you're like, well, how do I know if it's going to be quadratic or quartic? And that we'll figure that out very, very soon. But then now you should know what cubic functions look like. Okay, now just a few definitions to kind of go through because we're going to have to talk about this. We need to know what turning points are in the graph. Turning points. And I hope that seems pretty logical to you. It's when the graph changes from increasing to decreasing or vice versa. Oh, vice versa. When a graph changes, so like just looking up here, I went from decrease to increase. Oh, I had one turning point. Here, I went from a decrease to an increase, that's 1, back down to a decrease, that's 2, back up to an increase, that's 3. This is 1, 2, 3 turning points. So that's by definition what a turning point. You're going to have to find those tonight. I'll show you how. Local max and local min. Now we've talked about max and min before, but we've never talked about what a local max and a local min is. So a local max is it's a high point on the graph, but it's not the highest. High point on the graph, but not the highest. So like looking at my picture right here, this would be a local max right there on that W. He's a high point, but he's definitely not higher than this point right here. Because I'm keeping going to like off to infinity, so he's not higher. This one is the max, but this one is a local max, if that makes sense to you. Local min is a low point on the graph, but not the lowest. But not the lowest. Okay? Low point on the graph, but not the lowest. And then one more quick definition you're going to hear of is extrema. Like it'll say, find all the extrema. What they're all, the only thing, don't worry about that word. It just is, it includes all local maxes and mins. You include all the maxes, all the mins. Those are all your extrema. Okay, and that's what you'll see as some definitions tonight. So you might have to answer some questions about turning points. How many turning points does it have? How many, does it have a local max? Does it have a local min? And I'll give you an example of what you'll see on homework tonight. All right, so let me, that kind of is see-through, so I'll go over here. All right, so let's just do an example. What are they going to give us? And they're actually going to do it just like this. I double checked on homework just to see. I'm like, is this how they do it? But this is what they do. So they give you a graph like this. And they're going to label this as point AB, this one as point CD, and this one. They're not even going to tell you the points. They're going to actually give it letters, E and H. And then they'll give another one. This one is JK. And this one is MN. And they want you to identify and classify the local extrema. Identify and classify so say local min, local max, absolute min, absolute max. Okay, so hopefully this is easy. Again, here's that W shape. So we know this is quartic. Here's that cubic shape. So out of all these, we'll start with this one right here. This is a low point on the graph. Notice I'm decreasing, so I'm going down there, but it's definitely not the lowest on the graph, because if I kept going, I'd have a lower point. So this definitely, AB is a min, and it's a local min. This one's a min, but this is a local min because it's a low point, but it's not the lowest point. CD is up there. It's high. It's like on the top of that little bump, but it's definitely not the highest point because these arrows go up. So there's more points up here that are definitely higher than this point right here. So I would call this is a max. It's a local max though, because it's not the highest. Now, as I'm going down, now I'm at this point EH. Is there anything below me? This is a min again, but is there anything below me? No, this is an absolute min EH. So again, mins are low points on the graph. Absolute min is the lowest point on the graph. That is the lowest point. There is nothing lower than him. All right, we're moving over to this picture. Here's JK. He looks like a low point, but if I kept my pen going, it would definitely keep going down, which means there's more dots below him. So again, he's a min, but he's not the absolute min. So I'm going to put him in the min category, JK. And then this guy is definitely a max. He's on top of the mountain, but is he the highest point ever on that graph? No, there's way more points up here as the graph keeps going and going and going. There's this point right here would be higher. There's so many points, so we know he's a max, but not the max, MN. So there's no absolute max or none. And like I said, you have a question just like that. It's super, super simple. If you can just, concentrate on if it's a low point, if it's a high point, if it is the lowest point, is it the highest point? And that would be the difference between being an absolute min and max as opposed to a local min and max. All right, now let's go back to turning points for a minute. How do we find the number of turning points beside just, counting the curves? Well, there's a little theory here that the number of, it's not theory, it's true, turning points, the number of turning points of the graph of a polynomial function of degree n is at most, underline that, n minus 1. The number of turning points of the graph of a polynomial function of degree n is at most n minus 1. And let me just give you some examples of what I'm talking about visually. If I gave you this and I said this is a degree 2 polynomial, this is a quadratic, we're familiar with that. This one is a degree 4 polynomial. And this one is a degree 3 polynomial. The question will be something like, well, what's the most amount of turning points that it can have? All you do is do 2 minus 1. So the most amount of turning points that this of degree 2 could have would be 1. A quadratic can only have 1 turning point. It can only change from increasing to decreasing 1 time. Okay? A degree 4 polynomial can have at most 4 minus 1 or 3 turning points. Now you're looking at that picture and you're like, but there doesn't look like there's 3 turning points. Right, that's the most it could have. But this actually only has 1 turning point. Okay? I didn't want to write it like that. I was trying to show you that that's the most it can have, but it does have one turning point. It doesn't have to have 3. It has to have, at the most it can have is 3. So that's why this is a degree 4, but it has only one turning point. This is a degree 3, and it has 3 minus 1 turning points, so it has 2, and this one definitely has 2. 1, 2. My pen turns. So again, just so you know, that's what you're looking for with turning points. It's not necessarily they're going to have that many turning points. All degree 4s have 3 turning points. 4 minus 1. No. The most they can have is n minus 1. But you still look at the picture to determine how many it has. Okay? So watch out for that on the homework tonight when you're looking at the graphs. All right. And next concept is something called end behavior. I've literally been teaching this to my own students at school. So forgive me if I feel like I've already taught it before to you, and I'm like, oh. So there's this idea of end behavior of graphs. It's really neat. All even degree polynomials. So actually, let's make a chart here. Just make 4 spots. You'll see why. If you're even degree, if you're like ax squared, ax to the 4th, x to the 6th, on and on, x to the 8th, anything like that, even degree. The ends of all even degree polynomials, no matter what they look like, the ends go like this. Up, up. I mean, there's all this like stuff in the middle. Like if it's a degree 4, it could be a W, so it could go like, no, and then come back. But it always will start up and end up. And the way that we write it, we say as x becomes more and more negative, as x goes to negative infinity, our y values, our f of x, is going to be going to positive infinity. Our y values get larger. That's what the ends are telling us. They're going up, up. As x goes to positive infinity on this side of the origin, f of x also still goes positive. They go up, up. Well, if I change that a coefficient right there, and I make it a negative a x squared, and a negative a x to the 4th, and a negative a x to the 6th, etc., etc., what is going to happen? What happens when I have like a negative function? We've talked about that when we did all those transformations. A negative x squared. What happened to it? It flipped upside down. So now my ends go like this. The ends of the graph. They go down, down. So as x gets more and more largely negative, your y values also become negative. As x gets more and more largely positive, your y values get more and more negative still, because they're both going down. Your y values are getting larger because the ends are going down. So that's what happens of an even degree polynomial, an x to the 4th, an x to the 6th, x to the 8th, x squared, all of them. What if I had an odd degree one? So an odd degree follows just like ax cubed, ax to the 5th, etc., ax to the 7th, all the odd degrees. Odd degrees start down, and then they do something in the middle, and then they go up at the end. Down, up. So the way we write this is we say, again, this is the left side of the origin. So as x is getting more and more negative, your f of x is going down. It's getting more and more negative. As x is getting more and more positive, your y values are also getting positive. They're going up. Down, up. Easy. What happens if we put a negative in front of the a? Negative ax cubed, negative ax to the 5th, negative ax to the 7, on and on and on. Well, we know what happens. So we're just going to switch. Just going to go like that. My ends on the left of the graph will start up, but it'll go to the right and fall down. So as x becomes more and more negative on this side, f of x becomes positive. And as x becomes more and more positive, f of x becomes more and more negative. Okay? So how are they going to ask you this kind of question on homework tonight? I will show you. So the whole point being, you don't need to even really graph it right now. You should just be able to look at the leading coefficient and then look at the degree, and you should just know which one of these 4 it's going to be. It's always going to be one of these 4. Okay? So let me show you some examples. The end behavior of. And I'll do a few of them. P of x equals, that's a p squared. Okay. So here's just 3 examples of them. I mean, don't waste your time graphing. You're like, I just don't get it. Please watch, and I promise you it'll be so easy. Okay? Looking at this first polynomial, the square root of 5x cubed plus 5x squared minus 3x plus 2. Okay, you go and find yourself the leading coefficient right there. The degree with the leading coefficient, the highest degree, the leading coefficient. That leading coefficient is positive, right? There's no negative there. It's an x cubed, so it's odd. So it's going to start down and end up. It's going to go down, up. And then you just write this with it. As x is negative, y is negative. As x is positive, y is positive. That's it. And actually, these are the pictures they'll give you. I mean, it's kind of crazy. When I looked at homework, I was like, oh yeah, I forgot that it does that. It just gives you these pictures of arrows going, does it go down, up? Does it go up, up? Does it go down, down? That's what they'll give you. So it's really easy to look for. But you have to find the highest degree. So let's look at this middle one. My highest degree is the x to the 4th. Circle it. Circle the number in front with its sign. Oh, it's got a negative. Negative. Okay, so a negative x to the 4th, down, down. Down, down. So then you'd write this stuff. If x goes to negative infinity, y goes negative. If x goes positive infinity, y goes negative infinity. They're both down, down, both negative. The ends will become negative. What about this one? 3x squared minus pi x cubed minus 7x. Oh, they switched it again. They put the x cubed, that's the highest degree. There's a 2, there's a 3. So let's circle that. Oh, they scared us with a pi. Don't get scared. Pi is just 3.14. You know, square roots are the same. Okay, so it's a negative cube. It's a negative cube. So we go over here, negative x cubed would start up and end down. Up, down. And then you can fill out. Again, this is the highest degree. Look at your leading coefficient. You've got to look for that. Highest degree leading coefficient. Easy peasy, lemon squeezy. All right, almost done. Wow. This is a great lesson. We want to talk about number of X-intercepts. Number of X-intercepts. And I'm going to give you some pictures right here. Put some arrows here. Okay. I have just drawn for you a cubic function 3 different ways. And from these 3 different rates, these are all degree 3s. This is a degree 3. It's a cubic function. This is a degree 3. This is a degree 3. So what I want you to notice is how many X-intercepts it has, because if you know how many X-intercepts it has, you know how many real zeros it has. I've talked to you about this before. Zeros and X-intercepts are quite synonymous, okay? If a function has a 0, a real 0, then it has an X-intercept. If it doesn't have a real 0, it could have like an imaginary number, then it won't intersect the X-axis. So when I'm looking at this degree 3 right here, I can see that it intersects the X-axis at 1 point, which means it has one real 0. 1 point where it's crossing the X-axis, that means it has one real 0. This one right here, this cubic function, it is touching right here, and then it's crossing right here. So this actually has 2 real zeros. This one crosses the X-axis at 3 spots, so this has 3 real zeros. So what does that mean for us? Well, here's the idea behind that. That a polynomial of degree n, let's say, will have at most, there's that most again, n real zeros. So just like I had here, this is my degree 3 polynomial, 3 different ways. It doesn't always have 3 real zeros, but that's the most it could have. A degree 3 polynomial cannot have 4 real zeros. The most a degree 3 polynomial could have would be 3. It could have 2, it could have 1, but the most it could have would be 3. Okay? So you want to make sure, like if I gave you a degree 5 polynomial, look for the question, it'll say, what's the most amount of real zeros it could have? It could have 5 real zeros. What's the most amount of turning points? The most amount of turning points now would be n minus 1, 5 minus 1 or 4. That's the most amount of turning points it could have. And we're going to do that right now with our last question. We're going to determine an appropriate window. And I'm going to go to Mr. Desmos for this because it's so much easier if it works for me. If it doesn't, I'll revert back to my TI calculator ways. Graph y equals x to the 6th minus 36x to the 4th plus 288 x squared minus 256. I'll give you a minute to write that down. And before we graph it, just want us to talk about a few things, what this whole lesson has been about. I think it's important. Okay, so here's where my eye goes to right away. This is a degree 6 polynomial, okay? Degree 6 means the most amount of real zeros it could have would be 6 real zeros. That means it could intersect the x-axis up to 6 times. That's the most. How about turning points? Let's talk about turning points. The most amount of turning points it could have would be 6 minus 1. So it could have 5 turning points. That's the most. Again, these are the most. Not necessarily it will have it, but that's the most it could have. Okay? And one more thing I can get from this picture is the end behavior. I'm going to call it EB. So degree 6 polynomial follows the degree that's even, like a squared. So if I go back to my little picture right here that we did on before, even degree, ax to the 6th, ax to the 4th, whatever, it will go up, up. It's going to start up, it's going to end up. So my end behavior is going to go up, up. Okay, so now, come on, Desmos, work for me. Let's go to Mr. Desmos. Let's type this in. Y equals x to the 6th minus 36x to the 4th power plus 288x squared minus 256. Okay. There we go. That looks absolutely hideous. Look at that. I don't even know. Like, I'm just looking at a bunch of lines. First of all, I can see some intersections here, which is kind of cool. So I can see it's hitting 1, 2, 3, 4, 5, 6. Okay, it hit the x-axis 6 times. So it has 6 real zeros. There they are. That's crazy. Now, we got to determine a good viewing window right now. So a couple ways to do this is I kind of zoom out. I mean, and it just gets really ugly from there. And I just try to look to see if there's like a max or min. I can kind of see there's a break right here at like 250. Goodness gracious. Oh, there we go. So it's kind of down here. Oh my gosh, all the way at negative 1,000. I'm going to click on it. So 4.3. 4.3 is my x. So that means my x window is quite small. And then negative 921 is my y. So if 4.3 looks to be my x, I'm gonna go to this little wrench, and I'm gonna go to where it says x-axis, and you can see right now it's got a very large number. I'm gonna try to delete this number. And 4.3, I don't know, let's make it, negative 10 for the x. And then let's make the, ooh, I saw something. Let's make the other x 10. Look at that. That looks pretty good. They actually kind of fixed my y for me, surprisingly enough, while I did this. Because I saw that the y was going to go down there pretty tightly. But look, right here at negative 1,000, I'm actually going to make it negative 1,000. And I'm going to make the max. Where do they have? Make the max 1,000. That's pretty good. I like what they're doing here. Now, here's what they mean by determining an appropriate window. In an appropriate window, you want to see all the turns, as you can see here. Look at all my turns. I want to see all those local maxes and mins. Look at all them local maxes and mins. Here's an absolute min at negative 4.351, negative 921. Here's another absolute min. You can have 2. Here's a local max, 2 local maxes. Here's a local min. We saw our x-intercepts. Look at our end behavior going up. This is what you want to see. You want to see in an appropriate window that shape where it's intersecting the x-axis. I mean, honestly, we probably could have made this. I made it -10 to 10. You probably could have even made it like -8 to 8. But oh my goodness, I'm trying not to love Desmos as much as I am, but this is beautiful because this just did it so quickly for me. Honestly, I would have had to really zoom out to figure it out on my calculator. But this was really, really nice. So I'm going to say my window scale. Let me go back to my writing here. So I had it looks like I had an X min of -10, an X max of 10, a Y min of, I think I did -1,000, and a Y max of 1,000. And let me see what it went up by actually. It's kind of going up by 500s. I would go up by like a scale of 100s maybe if I was in my graphing calculator. And then you can just, you know, sketch it. I think they're actually going to make you sketch that little graph right here, but it was, let me look, it was down, 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 like that. Something like that. So that was pretty neat. Yay for Desmos working for me. Good. All right. Well, 6:42, and I am done with this first lesson.